this is trying to describe the oscillations here. And so typically when we think about it, it goes plus, minus, plus, minus, plus, minus, that kind of thing. So 1 second is positive, the next second is negative. And these waves, these oscillating fields, these waves are moving. And in fact, electromagnetic radiation, which is light, we call it light. Light equals electromagnetic radiation. We don't have to get into the details. We just know it's waves, oscillating waves. And so here it's oscillating more rapidly. Over here it's oscillating less rapidly because light, all light moves at the same speed. It doesn't matter what kind of light it is, and there are many different kinds of light. The light that we see is called the visible spectrum. This comes from light bulbs or light sources or the sun. The visible spectrum is just a small portion of the entire electromagnetic spectrum here. And you can see this is it. If you look here, we have all the colors of the rainbow, but it's still small. Then it's blown up here. Over here, it's not oscillating very fast. We have called radio waves. Then we have microwaves, infrared. None of these we can see. Then visible, which we can't see, ultraviolet, which we can't, X-rays and gamma rays. And what's the difference? Well, the difference is how fast those fields are oscillating. How fast those fields are oscillating is called the frequency. And so over here, with gamma rays, we have very high frequency of oscillation of these fields here. Over here, in radio waves, we have a much lower frequency. And what you have to do is you have to imagine this light wave moving at the speed of light. And so whether it's radio waves and gamma rays move at the same speed. The difference is in their oscillation or their frequency. Now, another way of understanding this is, this frequency of oscillation can be described in terms of wavelength here. If we look at gamma rays, the wavelength is the peak to peak or the valley to valley distance. And so you can see these peaks are tightly spaced. And so the oscillations happen quickly. Over here, the peak to peak distance is a lot longer. So if this is moving at the same speed, radio waves would be oscillating like this. Whereas gamma rays would be oscillating like this. They're both moving at the speed of light. So that's a little bit about light there. There are some equations regarding light, and that is this. So here, you see that symbol here? This is the Greek symbol lambda. What do we use lambda to describe? Do we use lambda to describe the frequency? Or do we use it to describe what we call the wavelength, the peak-to-peak distance? Well, this lambda is describing the peak-to-peak distance. So we got to imagine these two waves moving at the same speed. This one has a longer wavelength, this one has a shorter wavelength. If they're both moving at the same speed, these two arrows should be the same. I don't know what they are the same. But the speed of light is the same. And so if they're both moving at the same speed, this one's going to be oscillating a lot faster than this one. And so what this means is that a shorter wavelength equals a higher frequency. And a longer wavelength equals a lower frequency. And I define frequency this way. Frequency is defined as the number of cycles per second. So let's talk about frequency first. Frequency is given the symbol mu. It's shown here. Frequency is given this symbol mu. This is nu. It's pronounced u. The opposite of old. And so this is how many cycles, number of cycles per second. A cycle is a peak-to-peak cycle. So you start here, You drop down and you end back in the same spot. You go plus, minus, plus, back. Okay, the number of cycles per second is defined, as the hertz. The hertz, the definition of that is a cycle per second. The hertz. So if we go back to this and look at radio waves, you can see it's about 10 to the 6 to 10 to the 8. 10 to the 6 to 10 to the 8 hertz. 10 to the 6 is called a mega. And so radio waves are in the megahertz range here. Megahertz. Cell phones and microwaves operate around 10 to the 9th range, around here. 10 to the 9th would be called a gigahertz. And so your microwave ovens operate around the 2.45 gigahertz. Cell phones, Wi-Fi, in the gigahertz range, microwave range. Now, if you have megahertz, what is the wavelength? The wavelength is shown down here in meters. And so the wavelength would range maybe from 10 meters to 100 meters to even 1,000 meters. That means the distance from the peaks is 10 to 1,000 meters. If the distance between the peaks is 10 to 1,000 meters and you're getting 1 million of those come every second, that means light must be moving very fast. Because that's huge. The wavelength is huge on these, and yet the frequency is a mega, which is 1 million cycles per second, which is incredibly fast. And so we're going to talk about these in just a moment. We have wavelength, which is that peak to peak distance. Wavelength is given the symbol lambda, and this is just the meters, peak to peak. It doesn't have to be in meters. We can use other units too. Micrometers. So for example, in the infrared region, we don't like to use meters because it's 10 to the minus 6 meters. In the infrared region, if it's 10 to the minus 6 meters, how many 10 to the minus 6 is micro. So we like to use micrometers here. In the visible, we're looking at about 10 to the minus 9. In the visible, at 10 to the minus 9, 10 to the minus 9 is what? Well, milli is 10 to the minus 3. Micro is 10 to the minus 6. Yeah, it would be nano. And so in the visible, we don't like to use meters. We like to use nanometers. And so when we look at the wavelength for visible light, it's in nanometers here. All right, so this is light. Now, we need the speed of light. You know what the speed of light is? Speed of light is given the symbol c, and we'll just do it to 3 sig big. Okay, 3 sig big. Or 4. We'll do it to 3. Speed of light is 3.00 times 10 to the 8 meters per second. And then we have this equation here. Well, this is the speed of light, 3.00 times 10 to the 8 meters per second, which is 186,000 miles per hour. So that now makes sense. If you're going 186,000 miles per hour, then even if you have a 1,000 meter wavelength, it's going to come by very fast. So that's the speed of light. All right, now we have this relationship, this equation that relates these things right here. Do you see that one? C equals lambda nu. And so the relationship between these is this. C equals lambda times nu. And you have to remember, this is a constant. The speed of light is a constant in a vacuum. So we'll just say it's a constant here. So that means if one of these goes up, for example, if lambda goes up, the wavelength goes up, the frequency must go down, vice versa. And so in other words, if the wavelength goes up, then the frequency must go down. It's an inverse relationship, etc. So we can do calculations solving for one or the other. If you know the frequency, you can figure out the wavelength. If you know the wavelength, you can figure out the frequency by using this equation. I'm not going to do any calculations yet. We'll do the calculations at the end. And so if I want to solve for wavelength, wavelength is just equal to C, which is, you look it up, over nu. Or if I want nu, it's just C over lambda. Now, energy of light we need to talk about. So let's talk about energy of light next. Here. Do all these have the same energy? No, they have different energies. So for example, radio waves versus gamma rays. There's a huge difference in energy. Which one do you think packs more punch, radio waves or gamma rays? Gamma rays. Same thing with X-rays. In fact, gamma rays, X-rays, and UV pack a lot of punch. Gamma rays, X-rays, and UV are what we call ionizing radiation. They create ions. So they have enough punch that when gamma rays, X-rays, or UV interact with matter, they have so much energy they can knock electrons off and create ions. Do you think radio waves have enough energy to knock electrons off and create ions? No. But you know what radio waves can do? Radio waves can excite electrons. How do radio waves excite electrons? Like, in the old days they used to have metal antennas that stick up out of the car. Some of these antennas, they break off and people would use coat hangers or something like that. They tried to use metal coat hangers. Have you ever seen that? Maybe, maybe not. Could they use a plastic coat hanger to do it? Why not? Yeah. The reason is it doesn't conduct very well. You got to use metal. Why do you got to use metal? Because electrons in metals are loosely held. The electrons in plastic are tightly held. And so when an oscillating field comes by, wave field, what happens is electrons in the metal can start oscillating with the field, because electrons are negatively charged. And so the field comes along like this, electrons are in the metal, they start oscillating at the same frequency. Right? That's what we want. Whereas plastic, the electrons are so tightly held that the radio waves come like this and they can't budge the electrons in the plastic because they're too tightly held, so the electrons in plastic don't start oscillating with the electric field as well. And so typically this is what we say. Radio waves have enough energy to excite electrons in metals. It can, it depends on how intense the radio waves are. It can lead to things getting quite hot, etc. But what happens if you put metal inside a microwave? Have you ever tried to put metal inside a microwave? It's not good because it's too much energy. Too much energy, what happens to the electrons if there's too much energy? they get ionized. Have you seen sparks happen? Yeah. And so this is too much energy. So microwaves, you don't want to put metals in microwaves. The same thing with glazes. You know, there's when you have metal atoms, like, so for example, if you have a glaze, a ceramic glaze, so you put a ceramic mug in your microwave. The ceramic mug has, let's say, some of these metals, like whatever, some of these metals used in the pigment, right? And so if there's a metal atom with a lot of electrons in the pigment, that glaze is going to get super hot because the electrons in that metal atom start to get excited. As they get excited, create kinetic energy, generate heat. All right, so what we say is this. Radio waves can excite electrons. Microwaves, you know what microwaves can do? Some molecules are what we call polar. That is, some molecules will have a positive end and a negative end. Water, for example, is polar. Let me just do this as a sign here. And so the water molecule, it turns out, and we'll see this later when we get there, it's like this, and it has this kind of shape like this. But it turns out that one end of this is negative. It's not a full negative charge, it's just what we call delta minus. This is lowercase delta. And the other end is delta plus. Now, if you have an oscillating field, plus and minus, what's going to happen is that molecule is going to feel it. You know, 1 second the field is positive. If it's positive like this, then this negative is going to be attracted, so it's like this. The next second is negative, like this, right? And what that does is it causes the water molecule to rotate. And so what microwaves do is they cause water molecules or small molecules to rotate. They have just the right energy to cause this rotation. Infrared.
Is that just kind of like it's like just microwave work in general? Like that's how they create heat?
Yeah, right.
It rotates the molecule.
Rotates the water molecule, causing collisions and kinetic energy, heating up the sample. Microwaves are very efficient because it's just plugging in the amount of energy required for rotation. If you were to heat this, we'll talk about the next one, infrared. If you were to heat this in infrared, under an infrared lamp, it's not as efficient at all versus microwave. Microwave is just the right amount of energy to do this rotation, so we aren't wasting a lot of energy. If we put this under an infrared lamp, we're going to waste a lot of energy because water molecules aren't going to absorb all that infrared. What's going to happen is this. Not only does the molecule itself polar like this, it has a negative and a positive. When we're thinking about polar, we always think about like dipoles. Dipoles will have a north pole, south pole, positive pole, negative pole. That's 2 poles. There's also things called quadrupoles. Quadrupoles will have 4 poles, like 2 north poles, 2 south poles, etc., etc. And so when we're thinking about polar, we're thinking about this, you know, either north, like magnetic, north-south, or we're thinking about positive, negative in terms of polar. Well, normally we think in terms of positive and negative. So here we're going to think of that case here. Positive. But not only are the molecules themselves polar, but the bonds here, you know, what's linking the atoms together are also polar as well. And so if there's an oscillating field, then this is going to feel it. And so microwave doesn't have enough energy to do this, but infrared has enough energy to cause the bonds to start to vibrate. And so infrared causes vibrations. Microwave causes rotation. And so infrared, here, well, it turns out there are only so many ways a water molecule can vibrate. And so even if you heat it up over a flame, a lot of that energy is wasted because there are only 3 ways that the water molecule vibrates. And so only a small fraction of the energy is absorbed. But we'll talk about that later. And then we have visible next. Okay, what visible can do is visible excites electrons in matter. You know, it has enough energy to excite electrons along with matter. And so, you know, things, the colors originate because of shining visible light on the Visible light, do you know a good source of visible light? The sun. So if we shine all colors of the rainbow on this, then we can excite electrons in here, and that's what causes color to occur. Same thing with this black cable. I mean, if there's no visible light shining on this, there would be no color. So this is the visible spectrum. This is enough to excite electron in matter. But when we get to UV, X-rays, and gamma rays, it's too much energy. And UV breaks bonds. It excites electrons too much. And these bonds are held together by electrons. We'll talk about that later. X-rays and gamma rays knock electrons off atoms. And so their energy, from low energy radio waves to high energy gamma rays. So we should know the electromagnetic spectrum. Electromagnetic spectrum, we go like this. We could go from low energy radio. I'm going to go backwards from this. We'll start off with low energy. Low energy means long wavelength or short wavelength? Long wavelength. Long lambda. Low energy means high frequency or low frequency? High frequency or low frequency. Low energy means low frequency. It doesn't oscillate as much. Radio waves don't oscillate as much. Okay, from radio we go to, just follow along. We go to microwave, which will be a little higher in energy. And from microwave we go to infrared, which is abbreviated IR, IR for infrared. And then we go to visible. When we get to visible, then different colors of light will have different energies. And so we should memorize this mnemonic, which is Roy G. Biv. This is all the colors of the rainbow. Roy G. Biv. And so it goes like this. We start off with red, and then we go to what? Orange. And so red will have lower energy, longer wavelength, and lower frequency than orange. And then we just go on. Y stands for yellow, and then G is for green, blue, B, indigo is I, and V is violet. Red, orange, yellow, green, blue, indigo, violet. We should, it's probably a good idea to know the just approximate wavelength range. This is 700. It says 700, but it's probably a little farther out. But to be consistent with your book, I'll go 700. It's closer to 800 though. 700 or 800 to 400 on the low end. I don't want to. I'll just do it this way. It's going to be in nanometers. So it turns out, frequency is a bit of a pain. The frequency is 10 to the 15. Do you have a metric prefix for 10 to the 15? No, there is one, but we don't need to know it. And so it's a little easier to talk in terms of wavelength. And so violet will have the shortest wavelength, around 400, and red will have the longest wavelength, around 700 nanometers. Remember, the longer the wavelength, the lower the energy. So I'm kind of going backwards here. These are red, orange, yellow, green, blue, indigo, violet. Okay, then progressing along here, from visible, we go to ultraviolet. And so this is the way we remember. Infrared, this is before red. Ultraviolet is after violet. So ultraviolet, we can't see. And in fact, none of these lights we can see except for visible. We can detect visible with our eyes. Although we can't see UV, I guess bees have adapted so that they can see UV. Bees' eyes can detect ultraviolet. However, bees can't detect red. So that's visible to UV. UV is getting higher in energy, followed by X-rays, higher in energy, and the highest energy would be gamma rays. Highest energy. And so these, again, we call ionizing radiation because they can create ions by knocking electrons off. They have so much energy. And of course, electrons are going to interact with light. Why do electrons interact with light? Why do electrons interact with light? Two reasons. One, electrons have charge, right? And electrons don't weigh much. They don't have much inertia, right? And so they can be excited. Whereas a nucleus has charge, but a nucleus is much more massive, much more dense. And so is a nucleus going to oscillate like this? No, it's the electrons that are going to be interacting with light. And so this is talked about in your book, but you know what this is? This diagram, what this is showing? This is showing what we call a spectrometer. The spectrometer is used for spectroscopy. So I want to talk about spectroscopy. Spectroscopy, what that is, it's a measurement of the interaction of light and matter. Spectroscopy. And how do you measure? You measure using a spectrometer. So it's measurement of light / matter interactions. Measured using a spectrometer. So let's look at some of these measurements. These measurements are going to result in something called a spectrum. You know, I'm deviating from the book a little bit in the order of presentation, so I'm trying to show you. So this here is the spectrum of this. And so what they're doing is they're taking white light and shining white light into the spectrometer. And what you're getting out is this rainbow spectrum here. You're getting out that. And so what's a good source of white light? The good source of white light is the sun. And the sun is an excellent source of visible light. Probably why we adapted to see. Yeah. And so what we want to do is we want to look at the solar spectrum. The solar spectrum is going to detail the light and matter interactions here. And so let's take a look at the solar spectrum here. Oops. Okay, take a look, because not only do they want to know, you know, the types of light. The types of light were given here based on the what are they showing here? They're showing the wavelength. There's a typo here. It should be TH, not HT. In units of nanometers. And so you can see our visible light. Our visible light's around 400 to about 700. Yeah, well, anyway, 400 to 700. Most people can see out to 760-ish or so. Go below, a little bit below. So the solar spectrum, the most intense. Now this is the intensity of it. And the intensity is the quantity of light emitted. from the solar spectrum. And so if we see this, you know, the most intense portion of the solar spectrum is visible light here, all the colors of the rainbow. When you add up all the colors of the rainbow, you get white light. So when we measure the solar spectrum, we see this. We see all the colors of the rainbow, and we see this intensity. Although it looks like the blue portion is the most intense. Do you see that? The blue-green here portion is the most intense. Looks to be. Red-orange down here is on the shoulder. But you can see that this is less intense. On the other side of red here is what? On the other side of red is, what's on the other side of red? What do we call it? Infrared. On the other side of red is infrared. So do you see this is infrared here? Infrared's measured in microns. A micron compared to a nanometer is 10 to the minus 9, a micron is 10 to the minus 6. So this would be like 2 microns here, 2.2 microns, 1.75 microns. This is all infrared here. Infrared. And so it emits infrared. And then on the other side of violet is ultraviolet. And so if you look at the solar spectrum, there's ultraviolet radiation emitted as well. Some of this ultraviolet radiation is eaten up, you know, before it reaches the Earth. You know, if we go out in space, if we go out in deep space, is there any water, CO2, ozone out in deep space? No. And so if we're out in deep space, what we see is this yellow. But on the surface of the Earth, we don't see the yellow because it's been chopped up. How's it been chopped up? Well, water absorbs some infrared, you know. Does it absorb all the infrared? No, because water can't vibrate in all ways. So water absorbs chunks of infrared. This is why I say if you put it under an infrared heat lamp, you're going to waste some energy because water doesn't interact with all the infrared. Water is going to eat up this portion, it's going to eat up this portion here, this portion here, this portion here. So water is going to eat up some of that infrared energy from the sun before it hits us. What else is going to eat up some of that infrared energy? CO2. And then if we look closely here, there are other things that eat up some of the visible. And so not all the visible colors make it to us. We'll talk about that later. And then what eats up a good chunk of the UV ozone? So this would be from the ozone layer here. And so this jagged one, where lots of chunks are eaten away, is the solar spectrum on Earth. This one up here is the solar spectrum out in space. Okay? And spectroscopy is the measurement of light interacting with matter. In other words, this is the light that's being emitted from the matter contained in the sun. So, what does the sun consist of? And so people are going to go, okay, this is the spectrum that I see. Now, why is the sun emitting this solar spectrum here that we're observing? You know, what causes the sun to glow like a light bulb? I mean, why is the sun emitting all that energy? Well, one, the sun is like a giant nuclear reactor, fusion reactor, and a lot of energy is being produced. But what is causing this? What's causing this is in the sun consists of what we call the fourth state of matter. Did I talk about the fourth state of matter? Fourth state of matter is plasma. What is a plasma? Does anybody recall what a plasma is? A plasma is an ionized gas. Ionized meaning it formed ions. How did it form ions? How it forms ions are there's lots of kinetic energy. So if there's a big violent collision, it knocks electrons off. And so in the sun's plasma, there are what we call free electrons. And what happens with these is these electrons start to gain energy, as they gain energy, they can gain high energy like this, but they don't stay excited forever. Eventually, the electrons will cool down, right? In a way. As electrons cool down, you know, the first law of thermodynamics says that energy is neither created nor destroyed. And so what happens is, if the electron gains that energy eventually and cools down, that energy has to go somewhere. And you know where that energy goes? It's emitted as light. It's emitted as heat, infrared. It's emitted. And so what happens in the sun, you got a whole bunch of electrons. Those electrons get excited to all different kinds of energies. Some aren't as excited. Some are highly excited. And then you have everything in between. When you hit a certain temperature. Well, do you know the old light bulbs? The old light bulbs we called, not the LED, not the fluorescent, but these are standard old filament light bulb, which is called a tungsten light bulb or filament light bulb. And so what you can do is, okay, this is how the sun makes this light, is by exciting the electrons in the plasma, right? Well, you know, when you heat up a piece of metal, have you ever heated up a piece of metal? You feel it, you heat it up. I don't have any stainless steel rods. Metals have electrons too, but the metals electrons aren't as loosely held as the electrons in a plasma. Looks like somebody was burning some salt here. I don't know, there's some kind of contamination on the surface of this. You see, if there's some white crust on here, you don't know what it is. You know, it might be cyanide or something like that. Who knows what it is? Somebody used this. Needle valve to shut off the gas. Flame is a plasma also. So if I take this piece of metal and start heating it up, what's going to happen? It's going to get hot. Electrons are getting hot, right? It's kinetic energy. And so right now, I don't want to touch this metal because I can feel it. You know what I feel? I feel heat coming from the metal. Do you know what that is? It's infrared radiation. Infrared radiation is being emitted by the metal, even though I can't see it because infrared is invisible. But what happens if I continue to heat this? You know, I can heat it and it's going to start feeling warm, but if I continue to heat it, do you see that it's starting to glow? What color is that glowing? That's glowing red. And so not only do I have infrared, I still have infrared being emitted, but I also have red light being emitted. And what happens if I continue to heat this up to hotter and hotter temperatures? It's going to start glowing orange, yellow, and eventually it's going to get how hot? We call it, this is not going to be a red hot piece of metal. You know what this is going to be? It's going to be a white hot piece of metal. A white hot piece of metal is hot. And it's white because it's emitting what? When this goes white hot, it's emitting all colors of the rainbow. And so it's emitting, in other words, you know what? If I could get all colors of the rainbow, that's white light. And so I don't need the sun. All I need is a piece of metal. And so a light bulb, you know how a light bulb operates? A light bulb operates by passing electric current through the metal, tungsten, and exciting the electrons. And they get so excited that they start emitting all colors of the rainbow. And then we get white light. If we looked at the spectrum of a tungsten light bulb, we can see that. And so let's take a look at the spectrum of tungsten. There's a good one here that we can look at. We call these incandescent light bulbs. Incandescent. Actually, let me go back here. So you can see it here. Do you see it's glowing white hot metal? When it's glowing white hot, it's easy to oxidize. You know, metals are easy to oxidize. Do you know how they prevent the metal from becoming oxidized? How they prevent the metal from becoming oxidized is by filling this glass bulb with inert gas, like nitrogen. There's no oxygen in here. If there's oxygen in here, it'd heat up the metal, oxidize it quite rapidly. But anyway, you just heat up the tungsten until it starts glowing white hot. And so let's take a look at the spectrum. Oops, I didn't want that. I wanted the spectrum. Okay, that's not the one I wanted either. Well, you can see it at different temperatures. The difference between a micron and a nanometer is you move the decimal 3 over. And so this is visible between 400 and 700 nanometers, which would be 0.4 to 0.7 microns is what it is. But anyway, going back to this, here's the sun. You can see that the most intense portion of the spectrum for the sun is in the visible region. And here's the light bulb. An incandescent light operating at 3,000 Kelvin. The sun operates at 6,000 Kelvin temperature. At 3,000 Kelvin, which is our incandescent light bulb, it's mostly what being emitted? The most intense part of the light bulb emission is going to be most of the energy in powering that light bulb is being used to generate what type of light? What type of light? Well, if you recall, the shorter the wavelength, the higher the energy. And so this is all infrared here, and then from infrared we hit red all the way to violet here. And so it looks like the most intense portion of the incandescent lamp spectrum will be in the infrared. So it's mostly emitting infrared, not visible. And that means it's not very efficient, you know, for generating light. Now, you can buy fancier light bulbs, which I was going to show here, you know, different light bulbs, different sources for that spectrum. But anyway, so let's stop here. We'll take a break and then we'll continue.